right, guys, so last class we talked about solution, solutes, and solvent. And then we talked a little bit about solubility as we did that little mini lab. So today we're going to talk a little bit more about solubility and saturated solutions, and then take it a little farther into solubility curves. So before we get started here, we're going to do a little quick warm-up, matching some terms, making sure that you remember what we talked about last class, because I know it was about a week and a half, 2 weeks ago now. So take a little pause in the video and match up our terms. All right, another S word. Actually, let's go back. Solvent, remember? Somebody referred to that as, which I'm sure I just talked through this with you. Solvent refers to the greater amount typically. So somebody came up with a little reminder key of solute is a smaller word than solvent. So it is going to be the smaller part of the solution. So solute is smaller, which means it's going to be the solid or the smaller amount. All right. And then your solvent is the bigger word, right? So the greater word. And it is typically usually a liquid. Usually liquid. All right. And then universal solvent. Oh, no. I did not put the right terms on here. Universal solvent, we all know that is H2O. All right. And then solvation, remember we said that is just the scientific term for what you all know as dissolving. Something you've heard of all your life, but now we're going to put a fancy chemistry words in front of it and call it solvation. All right. So moving forward, another S word. We have thrown a lot of S words at you so far this unit. We have solution so far that we've talked about. We have solute and solvent, those that we just reviewed over as well. All right, so now we're going to add another one, and we've got solubility. Solubility refers to the maximum amount of substance that I can dissolve into my solution at a given temperature. All right, so solubility is how much is the max that I can hold at that temperature. So think about it. How sweet do you like your tea? How much sugar are you dissolving into your tea? And think a lot of times we have to change that temperature in order to dissolve more. We talked about how in restaurants, if you ever order sweet tea, how did they make that sweet tea? While the water was still hot and brewing the tea, then they added the sugar so that the sugar would dissolve easily. If you were to get a glass of unsweet tea brought to the table by accident and you tried to pour some sugar packets in, would it dissolve? Most likely it's going to take you a little while, a long time stirring, and then you might still have some grains sitting at the bottom, right? Because at a given temperature, different amounts will dissolve. So how sweet do you like your tea? Do you like it unsaturated? Meaning you have less than the max amount of solute. So I like to think of it as if we replace the word saturated with the word full, and you say it is unfull, then you have less than the max. If you go to the cafeteria and you say, I am unfull, then that means your belly did not get the maximum amount that it can hold, right? So unsaturated, unfull, your solution still has some more room for you to add some more. But if you go to the cafeteria and you come back and you say, I am saturated, or again, replacing that word saturated with the word full, I am full, that means your belly got the maximum amount it could hold. There's no more room for anything else, but you didn't overfill yourself, right? You got the maximum amount that could be held. All right, and then you have super saturated. So again, replacing that word saturated with the word full. All right, if you are super full, then you ate more than you could hold, right? So you went to the cafeteria and you ate and you ate and you ate and you ate, and you filled your belly up way past what it could hold. So that's what a super saturated solution does. We've heated it up so that at a really high temperature, it can hold a lot more, and then we cool it down. So now your solution has way more than the maximum amount of solute that can be dissolved at that given temperature that we've cooled it down to. Super full. So remember, if you think about the lab that we did, that was the solution that before the lecture, we went back and we heated it up and allowed it to dissolve so that during lecture, it cooled down to room temperature. So that was that super full solution, and then we heated it up so that it would dissolve all of that extra. And think about how unstable it was once it spit it all out. So when we refer to solubility in solutions, that higher temperature equaled higher solubility. All right. Supersaturated solutions are made at those higher temps and slowly cooled. So that's exactly what we did in our lab the last time we were in class. Again, remember what happened when we added just a little bit more once it had cooled down. It cannot permanently hold this. It all of a sudden suddenly released it and basically threw up everything else. So think about if you were overfull, stuffed yourself to the brim of food, right? Overflowing. And then you keep eating. Eventually what's going to happen, you're going to throw it all back up, all that extra stuff that you couldn't hold. So that's exactly what this solution does in a supersaturated solution. Once you add too much or you kind of disturb that supersaturated solution, then it spits it all up and releases it so that the solution is now simply saturated or just simply full. All right, so once it spits it back out, it is now just plain saturated. No more, no less. It's happy, content, full. All right, so one way that we can make the extra come out. So what you did in class the other day is you added a little bit more once it had cooled down, which disrupt the stability. But another way you can do that is with a seed crystal. So what we're going to do is we're going to flip and we're going to watch a YouTube video real quick. If I can get it to go back. Nope, I don't want to. Nope. Come back here. Bear with me as I figure this out. Here we go.
So we have a supersaturated solution. There's more that can normally be dissolved in there at room temperature. Very unstable. One way to get it to come out of its supersaturated state is just by vibrating it. Sometimes when I set it on the desk, that's enough for it to come out of its supersaturated state. Or the coolest way is by adding a seed crystal. So seed crystals of sodium acetate will allow those ions that are in a supersaturated state to recognize the crystal structure of these sodium acetate crystals, and they'll be attracted to it. And as that seed crystal gets bigger, more will be attracted to it. And as that gets bigger, more will be attracted to it, and exponentially gets larger until it goes back to its saturated state. Let me show you. Just a couple crystals. And if you zoom in, you might be able to see that sort of suspended in the middle of the solution there. And then those at the front of the room in just a moment will be able to see that begin to grow.
That's what you all saw during your lab the other day, but now it's on a greater scale instead of just being in a test tube.
So now, when that crystal finishes growing, what type of solution will I have again? So it's gone from supersaturated back to its... pick this up and just hold it at an angle for you. And you guys can see that there's much of the solution here. This part of it's completely saturated, isn't it? And you can see the large crystal that we made at the bottom. It looks almost like a solid chunk of ice, doesn't it? Now also, when you feel the bottom of this flask, it feels quite warm. And we'll talk about why that's so in just a sec.
All right, so that is what you all basically did in your lab the other day, but you did it by just adding a little bit more. Like he said, sometimes if it's super saturated enough, all it takes is just tapping it on the table and all of that will spit back out. So basically your solution just spit out all of the extra, and that fluid there that was up at the top, your solution at the top, was then just plain saturated, and all of that extra you saw sitting at the bottom was all of the extra solute that had been dissolved into that it no longer could hold at that given temperature. All right, so now when we talk about gas solubility, we're going to just add this quick point in as we're talking about solubility. Gas, all right, this is different than what we've been talking about. Gases are unlike liquids and solids, just what we've been referring to, such as your water and sugar, things like that. Gases in a liquid, think the carbonation in a soda, all right? Think carbonation in soda. What happens on a warm summer day when you go through the drive-thru, you get a, even if you get a soda with no ice, right? And you get a soda with no ice and you leave it in the car. Say you're out playing a game outside at the field and you come back and now your soda's hot. As the temperature increased, what do you notice about that soda now? Most of you, if you've ever tasted a hot soda, would know that now it is a very flat soda. Why is that? Because the solubility of the gas decreases. Solubility decreases for the gas. So therefore, not as much carbonation is in your soda as it was before, because as the temperature increased and got hotter, solubility decreased. And then for gases in a liquid, as the pressure increases, solubility would therefore increase. These are basically opposite of liquids and solids. For this one, think of the, what's it called? Soda streamer. How do the ones, if any of you have a little soda streamer at home, where you can put the little bottle up with just plain water in it, and then you push the top down and it carbonates it, how does it do that? It increases the pressure, and therefore solubility increases, and the gas is able to make its way into the water, and the solubility increases, and now you have a carbonated soda. All right, so when we think about gas solubility, think about carbonation in soda. So going back, that's just a quick input there for gas solubility. But now we're going to go back to talking about just our liquids and solids, which is mostly what we're going to talk about. You'll see 1 or 2 questions maybe about gas solubility, but for the most part, talking about liquids and solids together. All right, so taking solubility, and we're going to look at it graphed out and talk about what the graphs of solubility curves are actually telling us. So right here, this is an example of solubility curves. These lines represent the solubility of the substances that they're labeled with. So for instance, right there you have sodium hydroxide. All right, lead nitrate right here. All right, and so as you see, sodium chloride is this black line that goes about horizontally. So these are your different substances all plotted on one graph. What it is doing is helping you get a comparison for each of those substances and seeing how their solubility compares to the rest. Over here on the left side is the grams of that solute, so the grams of a given substance. So here we have, say we were looking at our sodium hydroxide, it'd be how many grams of sodium hydroxide can be dissolved in that 100 grams of water. The main thing that's important about this is you want to make sure that it's matching whatever it is that your question is asking. And so we'll talk about that here in just a second. Let me erase what I did right there. All right, and then down here at the bottom, we're going to talk about temperature. So as we know, solubility increases as temperature increases. Typically, you'll see some right here that are not very strongly affected by temperature. But for the most part, here you see these upward trends, whereas your solubility is going to increase as temperature also increases. So let's look at some problems with this. How many grams of sodium hydroxide, which you all should know is NaOH, remember from Unit 3, sodium hydroxide, will dissolve in 100 grams of water at 30 degrees Celsius? All right? So again, here's that 100 grams of water. Oops, that was the eraser. 100 grams of water that I mentioned a second ago. That is important right there because you want to make sure that it matches over here. If it matches, awesome. You can ignore it. No longer look at that 100. The only point of that is to make sure that these two match. All right, and they do, so we can move forward. So again, we said sodium hydroxide. Here's our sodium hydroxide line. And so that's what we're looking at. And it says how many grams will dissolve at 30 degrees Celsius. So we're going to go down here to my temperature and find 30. And you are going to follow it up until it intersects with that line. All right, so here's where it meets that line. That is going to tell us how much dissolves at 30 degrees. So I'm going to say that's right at 130 grams. So 130 grams of NaOH would dissolve at 30 degrees Celsius in 100 grams of water. All right, so all you're doing is finding that temperature and finding where it intersects the line of what you're interested in. Question 2, how many grams of sodium hydroxide, again, dealing with the same substance, here's our sodium hydroxide, will dissolve in 50 grams. What do you notice about this 50 grams? 50 grams of water, but what does this say? 100. So take note of that. We're going to talk about what that means here in a second. 50 grams of water at 40 degrees Celsius. So we're going to look down here at our temperature. Again, we're going to come back to this. We are looking first at our how many grams at 40 degrees Celsius. So temperature 40 degrees, following it up until it meets our line, and we're at 140 grams. All right, so 140 grams of NaOH dissolves in 100 grams of water. But this asks me about 50 grams. Well, what is 50? 50 is half of 100. So if 140 grams of NaOH dissolve in 100 grams, how much would dissolve in 50 grams? Think, you just have half the amount of water. If you were dissolving sugar in 100 grams of water, but then you cut away half of your water, half of the sugar would dissolve, right? So instead of 140, you have 140 divided by 2, so 70 grams of NaOH would dissolve in 50 grams of water. Again, this is half of 100, so then 70 is half of your 140. All right, so that's where this number is important. All right, number 3, at what temperature will 90 grams of PbNO3 dissolve in 100 grams of water? Here our 100 matches our 100. Awesome, we're good to go. We know that we won't need to make any adjustments. So let's look at the substance. First, we need to find what substance they're asking me about. Here's my PbNO3 too. And it says at what temperature. This time I'm looking for temperature and I'm given the grams. All right, so I go right here and I find 90 grams, which is about right there in between, and I'm going to follow it over. All right, and depending on how you drew your line and how straight you kept it, it intersects with our line of interest right here. If I follow that down, what temperature is it at? We're at 50 degrees Celsius. All right, so at 50 degrees Celsius, those 90 grams of PbNO3 will dissolve. All right, so something to note, these curves also help you know whether or not a solution is supersaturated, unsaturated, or just plain saturated. So any amount that is below the line, and we're going to see this in a few examples here in a second, anything below the line or under the line is unsaturated. If it's on the line, meaning your grams is right on the line, whatever your line of interest is, then you are just going to be plain saturated. Remember, we said it's full, not above, not below. It is just plain saturated. And then above the line, think about if you go above and beyond, you are super. All right, so if your plot lies above the line, you are going to be super saturated. So you're probably like, what in the world are we talking about right now? So let's look at some examples real quick. If 45 grams of potassium chloride are dissolved in 100 grams of water at 60 degrees Celsius. So let's take a second. Very important to underline your key words here. That way you don't get bogged down in all the words that are happening in your problem. So making sure that your 100 grams match. It does. Awesome. You are good to go. So I'm saying there is KCl. So let's find our potassium chloride, KCl here. And I'm dissolving 45 grams, which is about right here, at 60 degrees Celsius. So I'm going to follow those two lines until they intersect, which, if you look, here they are. And notice that point is where on that line. It lies directly where the line is. So on the line, remember, equals saturated. So my solution is saturated. So that's to say if I took potassium chloride, dissolved it in 100 grams of water, 45 grams of that potassium chloride at 60 degrees Celsius, my solution would be saturated. All right. Let's look at number 5. If 90 grams of PbNO3 is dissolved in 100 grams of water at 40 degrees Celsius. What is our saturation? So, what's our line of interest? Here we go, lead nitrite. Lead nitrite. And so then 90 grams, we're going to follow it over until we meet 40 degrees Celsius. And look where we're at compared to, here's the line of interest, but here's my dot. I am above the line. So that means I'm what? Here's the fill line. If you were at the gas station and this is the fill line in your car, if you went above the line, you are super full. Or remember, we replaced the word saturated with full. So super saturated. Oh, I'm running out of room, but super saturated. All right, so this solution here would be super saturated or super full. You're above the line. All right, number 6, another example. We have 30 grams of KNO3, 20 degrees Celsius. So let's highlight it. We're talking about KNO3 here. And we have 30 grams at 20 degrees. If I follow those over till they meet, here's my dot. It is again on the line. So think about if you go to the gas station, you filled it up right onto that line, you would say, oh, my tank is full, or just plain saturated, right? So here's your line of interest. Here's your dot. You're on the line, so you are saturated or just plain full. So if that's how much I dissolved at 20 degrees Celsius, then my solution is saturated. And last one here for an example, I have 10 grams of KClO3 and 50 degrees Celsius. All right, so find that line. Oh, that's the eraser. Let's find the highlighter. There we go. And now I'm highlighting the wrong one. KClO3. Make sure you're always paying attention to which one you're highlighting. Don't make the mistake Miss Simmons just did. All right, so 10 grams at 50 degrees Celsius. Here's our 50. Whoa, look, here's my line that I'm interested in, but here's my dot. All right, so let's use the gas tank analogy again. Here's my gas tank. If you go to the gas station and you fill it up and it ends right here, and now your hand doesn't meet the full line, you would say, oh, I am unfull, or I am unsaturated, right? So, because you are under the line, you are now going, this solution would now be unsaturated.